Good morning, ladies and gentlemen. Thank you for joining us today for the webinar titled Rules of Thumb for Geologic Modeling, presented by Eric Ronald. My name is Jackie, and I will be your host for today's session. Attendees may submit questions at any time during the presentation by using the chat panel. The host will read the questions aloud to our speaker during the question and answer period following his presentation. The creation of geological and resource models is a combination of art, science, engineering, statistics, and well-informed hypotheses. This webinar will discuss a series of critical aspects to consider in order to ensure models are both useful and provide a robust presentation of the deposit. Eric Ronald is a principal consultant with SRK Consulting in Denver. He has more than 20 years' experience in mining, mineral exploration, and resource geology. I'm now pleased to turn the session over to Eric. Will you share your screen with us, please?
Thank you for that intro, Jackie. Is my screen coming through?
Yes, sir, it is. Please proceed.
Will do. Well, thank you very much for that introduction. And hello and welcome to everybody who's attending today's webinar. Good morning to those in North and South America, at least on this side of the continent. So as Jackie mentioned in the introduction, the focus of this session will be to introduce you to a variety of items that really, if considered and performed well, aim to assure that a robust geological model is available and able to use in mining. I'm going to be talking about a lot of generalities of models with a focus on using geological models and really under the guide of the mining industry. So the topics and items discussed, they're not complicated, they're not expensive, they're not overly analytical, but are really important suggestions, items, and issues that I've personally experienced throughout my career that can honestly make or break the quality of a geological model. Some of these issues I'll be presenting, they're not unique to any deposit type, commodity. You see them across companies, large, small, and it really doesn't depend. It doesn't depend on a big world-class corporation, a small little junior, a consulting. These are common items that are seen throughout. So now let's get started here. All right, firstly, I want to set our scene as geological models. They're just not the products of what consultants do or what some dirty mine geologist does on site or just something a company that may feel they need to update their model every few years because somebody told them or they feel that they should. These models really form the foundation or the basis for calculating mineral resources and reserves. In fact, the block model is simply a means of determining quality and quantity within volumes, but it's based on that geological understanding added with some analytical data. Typically, you get that from drilling. That's the main input for these, of course. Now, mine planning's primary input in order to calculate economic volumes for reserves, perform designs, consider mining methods, produce a mining schedule, it is the block model. And the block model, if you remember, is essentially just a chunky representation of what the geological model is with estimated qualitative attributes to it. So lastly, we think from a business point of view, discounted cash flows, business plans. Now, these are all based on the economic outputs of the mine plan. That's essentially paired with sale prices, expenses, and so forth. So for most mining companies, especially junior companies and explorers, the rocks in the ground, I mean, these are the foundation assets of the business. Therefore, we should look and consider the geological model as really that business tool that's used to communicate and to understand, plus evaluate that primary asset of these companies. So what we see on the screen here, this is a typical workflow for calculating mineral resources. Each box here showing a different step in a process. to go from, say, basic field geology all the way through to a compliant mineral resource statement. So under the context of mineral resources, the geological model, well, it forms one piece of the roadmap. We see it highlighted there in yellow and red. That said, its weight within that is huge. Really, the assumptions and interpretations of the model are the foundation for all the downstream decisions on data analyses, estimation, classification, and so forth. For the purposes of this presentation as well, you'll notice I might use terms like geology or domain, and in a case like this, very interchangeably. So I want you to make sure that we're clear on some of the language. There's certain cases in which I'll talk about, say, an estimation domain that may constitute a geologic unit. It might be a grouping, or alternatively, sometimes domains we need to split out geology into subunits. But for modeling purposes and for the purposes of these rules of thumbs that I've put together, they apply throughout. Also, this talk is not about the merits of geostatistics or estimation methods or things of that nature. I really want to focus in solely on the modeling side. I find, and in my experience, that getting the geology right and getting your domains correct will really set up the whole process for a better model than trying to take something that you have to create a creative estimate because you're very poorly informed data, geology is not understood, or where you're forced to use, say, advanced geostatistical techniques to try to squeeze more data out of what you have. Really, the fundamentals are absolutely the foundation, and that foundation is the geological model. So we go back to understanding the rocks in the ground and how important that is. I can't emphasize that more, but the model is our way of communicating that understanding through all the business processes downstream. So this talk is about models. It's not about economic geology, so let's start with a little bit about models. I've always thought this was a very appropriate, and I always like this quote from the statistician George Box about models. All models are wrong, some models are useful. Simple quote, quite wise when you start thinking about it. The makers of models, the creators of models, typically the geologists who are the modelers, they tend to understand this concept better than a lot of the users of models, I find. So by definition, a model, it can't be the truth. It's a representation. It's merely our best guess based on the data available at the time. We aim to produce these useful models that'll help us to understand various geological properties or spatial attributes, distributions of grades, volumes, tonnages, or any variety of kind of quality measurements. And I'd include geotechnical, geometallurgical properties in that as well. So in order to consider a model as good, it must always be validated and verified. You need to ask yourself, are the assumptions put into the model what we're actually getting out, right? Where we've mined or where we've actually tested parts of the model. Did the model closely predict what we thought we were going to get, whether that's grades or tons or rock type or whatever attribute it might be? And ideally, that hard data is used to validate our model. That's really the only way we can validate these. Most commonly, this comes in the form of, for at least operating mines, production reconciliation, but at other times it's mapping, whether that's pit mapping or surficial mapping, maybe bulk sampling or just additional drilling, drill testing using different methods. Remember, if a model is validated, at least for, say, an area or volume or portion of the model, the hope is that the model will perform well for future predictions. Ultimately, that's the best test of whether we consider our model to be useful or not. So I like to start big picture, I think. And these really, we start and we look at that, they say the 30,000 feet level, the flyover. We look at models, there are no right or wrong. There's poorly and well-informed models. There's beneficial and there's certainly useless models. Really with the goal of geological modeling being to produce a well-informed, useful model based on that best available data, plus our interpretation, right? Now, model users and the customers, the people who are actually relying on these models, they must always realize that models change. They change with more information that's gathered and as they're used. Now, sometimes we drill, we test, the grades in tons go up. Sometimes they go down, but typically the more well-informed a model is, the more useful it is for understanding, for predicting, planning, and for ultimately decision making. Now, always keep in mind, a model is equivalent to, say, a working hypothesis. I think that's a good way to look at these, is that they're not the truth. Models done, updated in December, you roll it forward and that better work. Well, this is our best guess in December, and guess what? Next December, it might look different. Now, these are subject to change. We're always going to collect more data, whether that's mining or drilling or whatever. And we would expect, and we would hope in some cases, that these would be refined and change over time. Now, geological understanding and modeling in mining specifically is really about risk, understanding risk, and the confidence associated with this. The more data gathered, the more integration of geologic understanding, and also with mining and processing, the improved understanding of geology results in really more accurate model prediction, the increased confidence, and ultimately, this has increased the confidence of mineral resource categories, measured, indicated, inferred, and possibly unclassified. And overall, this is all to ultimately reduce the risk of a project and losing value. We all know mining is a very capital intensive endeavor, and appropriately understanding and de-risking the geology up front will result in direct improvements all downstream through optimization, performance, costs of operations, so on and so forth. Often we see between 3 and 5% of overall project costs spent upfront during studies. This could be PEA, PFS, maybe FS. Now that's quite low, but you think about the de-risking value of what you're getting out of it by pouring more money into geology. It comes out sometimes 10 to 100-fold. Now, alternatively, the risk involved with incorrect modeling or just not understanding that geologic area, really over or underestimation of your contained metal or the product that you're looking to mine. And if you overestimate that, then obviously there's an over and an underestimation of the valuation of the project. When you get down to the nitty gritty, to the details, not having correct locations for ore waste boundaries, which results in poor mine performance, economic loss, dilution, recovery issues. The list goes on, and ultimately result in a non-optimized mine plan, which means lost money. So one of the keys, I think, that geologists and resource modelers, for that matter, always must think of their work in terms of the broader business, in finance, in dollars, in value. It's great to say your geologic model is better, but communicate that to an executive committee or board of directors, and that may not mean much. That's quite subjective. So thinking about risks and modeling and geology in terms of financial value is absolutely key to communicate the importance of our models. So these rules of thumb that I've put together, now they're just for internalizing, they're for the modeler, the geologist, really to question what they're doing. These are some common issues that I've seen. They're certainly not prescriptive. It's not about, okay, do step 1 when you're done with step 1, move to step 2, so on and so forth. These are based on my personal experience. There's no analytical evidence that one of these items occur more often or whatnot, but I see them commonly. And again, it doesn't matter where you are internationally, whether you're in gold or construction aggregates or something in between, these are common things that are seen. Now, one thing in my role, I'm often asked, well, what's the best tool to use for geological modeling? And I always like answering this question because it's not a fancy software. It's not some whiz-bang implicit modeling type of thing that you push a button and some magic happens. It's your human brain, right? It's experience, it's knowledge, it's being able to take an understanding of what a software does, what it can do, cannot do, and applying your understanding of a geological deposit or area, whatever, and pulling it together to create this model. Now, these rules of thumbs, I've got 10 of them. If I tried really hard, I could probably squeeze a few together, and if I tried harder, I could probably expand them out. But I find 10 is kind of a nice number. So with these, we've got some simple items like understanding what the model will be used for, obviously knowing the geology, incorporating data, exploring the data, right? Really pulling apart, and this is where some stats come in. How we think about our deposit models or regional models, the importance of structure, and from a modeling point of view, realizing we're not trying to model everything down to the crazy detail. We need to keep it relatively simple. Now, we're in mining, at least most of us are probably in mining, so we all love the ore and the shiny stuff, but waste is awfully important as well. And then the implications of the 2D versus 3D modeling out there. And last, and you can argue most important really, but typically done toward the end, is verifying and validating our models, making sure all those assumptions went through. So I'll step through each one of these with a little more explanation and give some examples here. So first one, number one, what's the model going to be used for? Now, surprisingly, many geologists and modelers I speak with, they can struggle to answer this question, though it seems pretty straightforward. A geological model is created for a very specific purpose, and it's critical to have that clear understanding of what that purpose is prior to getting into interpretation and start modeling the geology. An example would be a model used for, say, early exploration drill planning. Now, chances are it's pretty poorly informed. You may not have a lot of information. You might just need a few basic outlines of, say, some alteration from field mapping, a bit of mineralization from, say, trenching or shallow drilling, and regional structure. However, a geological model, if you're going to be using one for, say, something more detailed like a metallurgical feasibility or plant mill development, now this is going to require vast amounts of detail, a lot greater detail, and a lot more data. Now, in a case like that, it might include complicated domained units based on a variety of things: petrography, comminution testing, chemistry, recoveries, and certainly deleterious attributes. And it may not actually resemble a geologic model or the geologic units in the traditional sense, but because of its specific purpose, we need to combine and pull apart. And that's where that expertise and understanding needs to come in. So it's important. I mean, it's critical really to, prior to getting started with a modeling process or updating for that matter, to agree on the scope, time frame, important attributes, and ultimately understand what decisions are going to be made based on the model. I mentioned time frame in there because that can be a lot of times the constraining factor of how useful a model is. If a model needs to be done in 2 weeks versus a model needs to be done 3, 4, 5 weeks or even months in advance, then a lot more detail and understanding can be put into it. So to give an example of this, let's consider a resource model versus a grade control model. Now, to a lot of people who aren't intimately familiar with models, they may say, well, these are kind of the same thing, right? It's all a bunch of block models or whatnot. But one of them is used to report and understand global mineral resources. This is over the whole deposit. While the other, it's to make short-term decisions on quality and quantity of material for mining and processing. Now, they're both models, and chances are they include similar variables, but really the construction, the uses, the methodology, and the scope are very different. So In the resource model, we ideally want to minimize conditional bias, and by smoothing out our drill hole grades across big volumes, we want to gain an insight into spatial trends, distributions, understand the amount of material that's above a cutoff grade. The way a resource model is created and estimated requires a focus on the big picture, knowing that locally it's probably not that accurate. In some cases, you've got very large blocks that are larger than your selective mining unit. Now, again, we move over to the grade control model. This is kind of the opposite scenario. We want to minimize smoothing, right? We actually want to potentially increase that conditional bias. We want to know as much on the small scale what the grade is doing and particular variables, so decisions can be made quickly as to whether the materials crusher feed, worth keeping or stockpiling or blending, or uneconomic waste, and to send it off to the dump. So rule number 2 is understand the deposit geology. Now, chances are most of the people on this webinar are geologists or related to geology, and you think, oh yeah, no kidding, this is a no-brainer. But I can't overemphasize the amount of importance this one has to be. It has to be high on the list, right? So the person, or more commonly the team involved with modeling a deposit, really must include an experienced and competent geologist who's knowledgeable about the site geology. Now, sometimes this is the same person who's actually pushing the buttons and doing the modeling. Sometimes this is more of an advisor or somebody who comes in and checks. Sometimes it's just part of a team. Depends on companies and sizes and so on. Unfortunately, we do see occasions out in industry where companies might employ a person who doesn't understand or have experience with that particular deposit, style of geology, or whatnot, and might be more of a software expert, or somebody who knows where the buttons are to push, right? And in these cases, they rarely end very well, I'll say that. And just because you know where the buttons are, you know how to operate a software, that doesn't necessarily make you a good geological modeler, right? It's the combination of the two. So a model must adhere, when making it, to all the geochronologic sequence of an ore body genesis. And most of all, it's got to make geologic sense. Now, who's the best person or team to do that? Typically, it's site geologists or exploration geologists. So the relationships of units, structures, alteration, and all the other features, they must be modeled in the same fashion, in the same order, while respecting those observed cross-cutting relationships, spatial relationships, things that you see in the field, the pit, underground. So an example of this, and we see this commonly, the spinning Leapblobs. So, this is a trap that I've seen across the globe in the mining industry, and I'd really chalk it up to misuse of software. Now, there are absolutely amazing and fantastic software packages like Leapfrog that they're commercially available and can relatively quickly produce a very shiny 3D wireframe. And it is based on the data using implicit modeling techniques. And this is honestly a fantastic thing. The advances of where we've come with Leapfrog and other packages like GoCAD and whatnot can't be it's just fantastic. But if you're knowledgeable of what the software is doing, you have to understand its capabilities, its deficiencies, and most importantly, understand the geology that you're modeling. Tools like Leapfrog can assist a competent modeler, if you're using the right tools, to get the majority of where they need to go in a relatively quick time. Now, using defaults, not knowing what you're doing, it's not necessarily a one-button solution, but somebody who doesn't really know what they're doing, they can produce something, but that's a dangerous thing. And for a truly useful model, you've got to understand the deposit geology and ensure the modeling makes sense. You see the little picture on top there with the little donut blobs floating off into space, and I don't think there's too many geologists out there who would say, yeah, that looks like that makes good sense. I like that. So honestly, I don't think there's anything more dangerous to mineral resource risk than somebody who uses a software that they flatly just don't understand, simply because it's quick, it's rapid, whatever, or it produces something pretty that looks good when you spend it in 3D. Software proficiencies, it's really required, along with that geologic knowledge to produce it. As I mentioned before, a lot of times these are done in teams, and so having an expert on the software sit side by side with an expert in the geology is probably the best way to do it. In some cases, it is the same person. So moving on to rule number 3, using as much data. Incorporate all the data, but trusted data. So there is another disturbing trend in the industry that I've seen where a lot of geologists may rely solely on drilling data to perform the modeling. Well, this is great because we like to call our drill the truth machine, and drilling is a fantastic way to get subsurface information for relatively cheap. And with the advent of the implicit modeling, like I was mentioning, even a novice can rapidly take a database that's well coded and generate a 3D shape. Alternatively, I've seen early exploration projects with only a few drill holes create an absurdly blown out volume of mineralization by ignoring other associated geological data. They just look at drilling and nothing else. So, as mentioned in one of the earlier slides, a geological model works best when it's well informed. And so what I mean by this is that a model should respect all existing data sets, and this would include things like surface mapping, geomorphic analyses, geophysics. In cases you've got trenching, of course, drilling data, as I've mentioned. Sometimes drilling data includes a whole lot of different types of drilling, different methods, or for different reasons, blast hole, water wells, things of that nature. If you're lucky to have an open cut or an underground mine, obviously the information there is fantastic, but don't forget to kind of take yourself back to when you first were learning about geology and mining, and that the value in some places of road cuts or public information, anything that you have some trust in can and should be used to be incorporated to use in the model or potentially to validate the model. Now, historic data sets, they can be absolutely golden, or they can be completely fraught with inconsistencies and inaccuracies. So it is important to have confidence in the data, but to the experienced person, I find that even data that might not be the most trustworthy, I like to point my finger at blast hole data, it can still be insightful because it can still be useful to gather limited data out of it. So for an example of this, I think this is a common problem that we see, and this example is specific to industrial minerals. But industrial minerals, and in a lot of mining cases, depending on the cycle, there's a lack of capital for improvement projects, especially related to deposit definition and collecting more ore body knowledge. So there was a project I was involved with. It was probably a decade ago or so, with an operation that we were seeing a lot of changes in the ore body at depth. Mine planning was out of date. The model was the same and in need of an update. Unfortunately, being industrial minerals, the margins were low. They were small margins, and so capital was tight, and there wasn't a lot of money to drill the deposit out at depth to really improve what our ability to predict going forward. So using a shoestring budget, a lot of public information, historic data that was all on smelly, crusty paper. This was digitized, was able to georeference in and bring in a lot of this previously interpreted or good information into the model that hadn't been looked at before. So this included some of the old historic pit maps, regional geologic maps, some fantastic detailed underground maps, and just a lot of kind of oddball technical papers from universities within the area. I also did was implement a new pit mapping campaign out there to collect essentially 3D contact and structural information, not to mention some material type information that was right in the high walls and in any any benches that you could actually access safely. So additional regional information, was able to get a couple things from some local road cuts. A lot of topographic analyses were done, lineament analyses. So there was a lot of information that was kind of already out there. It just needed to be interpreted and brought into the model. So it became this exercise of improving the geology to then improve targeting. And so a limited drill budget could be used because we were able to improve the understanding of the geology and actually really nail down where we needed the more information. So obviously this is a cycle process where these additional holes were then used to provide that much needed information on grade, tonnage, density information, and geology in these key areas of the mine plan to go forward. Then, of course, once we had all that drilling data, that was fed back through to the model that was already updated, and the whole cycle starts over again, and modifications to ore types based on future material, and that cycle went through. So it was a relatively low-cost endeavor that turned out fantastic just by being a bit more creative, I would say. So I'd mentioned historic data. Now, there's, I think, a couple different schools of thought. I would say new does not necessarily mean it's better, but obviously old stuff we need to take with a grain of salt. So when you're incorporating this trusted data into your model, you really need to consider how and what context it was collected. And in my experience, at least with a lot of geological data, and especially kind of older data, for instance, say geological maps done pre-95 or so. Now, these were done by hand, often in the field, on paper. I find that the time frames pre-95 were usually longer, meaning individuals, field mappers, were given more adequate time to actually work out geologic relationships and whatnot. Most of them, as I said, they were done in the field, so people are looking at outcrops or benches while they're making decisions right on that. Now, you kind of compare that to modern day work and in a lot of operations where we have small teams of geological mappers who may go out and say a pit or underground mapping, a lot of times done directly on tablets, which can be a bit confining. There's always time constraints, cost constraints. Data is also often collected by the least experienced person in the team. They throw the graduate or the vacation student out there. And so you kind of need to know some of this before you incorporate it in your model. Again, I'm not saying older data is always, better. I'm just saying, just don't toss it because it's on paper. Don't toss it because it's old. Data doesn't have an expiry date. And realize that often those older maps or sections, they were created with a lot more time, thought, and oftentimes by a more experienced person. So rule number 4, know the underlying data. Now, whether you have the luxury of a big, large, multi-source data set or just a small number of, say, grab samples on your deposit, be sure you interrogate your data to have a fundamental understanding of what's actually going involved. This is specifically exploration data analysis or EDA. And this is on categorical data, this is on numerical data, assay, descriptions, whatever it may be, to really understand, how do I group these things? What are the relationships? How do these relate to one another? They say there's 2 types of people in modeling, and these are the lumpers and the groupers, right? And whichever you may prefer, whichever situation might call for it, it's key to know the data and why you're potentially combining it or breaking it apart. And then understanding what decisions, business decisions, are going to be made on this model, right? Think back to rule number 1. So this will allow the modeler to best determine how the amount of data groupings or splittings that may be required, what's appropriate. And again, when I talk about splitting, it might be rock types, could be physical characteristics, chemical assays, mineralogical groups. The list goes on and on. There's a lot of different types that can be done. So when you start pulling the data apart, the devil's really in the details on this. If anyone's to ask me, well, what are some of the areas that God, if you had a little bit more time, you could probably get more out of it. Of course, geological understanding is probably first and foremost on that. But if I had to choose a close number two, I'd say it's the exploratory data analysis, really. Um, in reality, these kind of go hand in hand when you think about it, because the data trends and the behavior of your data, they usually can be explained geologically. But knowing these trends, attributes, and characteristics, it takes a bit of time, and again, pulling your data apart to really understand it. How the modeler determines a unique domain or grouping, that has massive effects on decisions for estimation down the road. So when you obtain a domain using common stats or statistical attributes, it's absolutely key. Additionally, the modeler should consider the types of geological domains that might be most useful. Might be a long list. You see some of them on the screen there, some of the different types of grouping that people are done. Again, this is understanding what it's going to be used for. Though it comes in more, I guess, down the stream in estimation, it's really good to consider about the boundaries of these as well. We use terms like hard boundaries. This would be, say, a post-mineral fault that absolutely truncates mineralization. Soft boundaries, like decreasing, say, alteration that diminishes over a distance, or even economic boundaries like grade shells or indicator shells that are based on prices of metals. So rule number 5, think globally, but model locally, right? And geological models should always be constructed, I believe, from a wide regional perspective first. Know where you are in the world. I think that's very important. Then modified and interpreted down to the smaller area of interest or the deposit scale. All too often, modelers, especially mine geologists, they interpret features or structures within an ore body incorrectly. I mean, it's especially when you compare it to what's going on outside the pit. That local scale complexity is really hard to work out when you don't understand the regional tectonics or that macro scale setting. So for example, say in a highly altered, deformed, like a skarn ore body, where you've got high concentrations of squishy soft minerals, chlorite, talc, nasty things that the Mets hate. These things result in really extensive, like soft sediment deformation when you get large-scale regional structures coming through your pit or through your mine. Pit mapping can be really complex. Structures can be discontinuous from one bench to the next. The whole thing can just be, absolutely do your head in trying to figure out what's going on. The structural controls on mineralization can actually, in many cases, be understood a bit easier if you get away from the mineralization. If you think about it, stepping out from a regional perspective to understand what should be happening. As some of these large regional structures may enter, say, a softer lithology or a highly altered area, they often behave like toothpaste, and it just goes everywhere, and you can't figure out when you're stuck in the middle of it. So, the micro scale structures, these can be absolutely tricky and do your head in. So I find stepping out is always a good thing. A quick example of this, this is a mineral deposit located in a fairly structurally complex and certainly active region of the world, the Mojave Desert in Southern California. The region's relatively flat. You couldn't find an outcrop to save your life. They've got out there what you like to call California bedrock, essentially poorly consolidated, kind of a bedrock regolith mix. It's just kind of a big pile of dirt, really. It's a stratobound deposit. We know there's offset faults identified from some of the historic underground workings and drilling and whatnot. But really that exact location of those faults, the attitude of them, the behavior of those faults as far as offsetting, it's absolutely key to understanding the ore body. By knowing the regional tectonic setting in a deposit like this, it's so key. So this one, it's a very well documented area. We're located in a big block between the right lateral strike slip fault of San Andreas and left lateral Garlock fault that butts up against the Sierra Nevada to the north. And so as a result of that, we should see northwest, southeast secondary faulting within this block for the most part. So if we understand what's happening regionally, we can kind of predict what these faults should be doing, what the offsets and likely displacements may be. We understand that. Now we can take that as a model and apply it back to our data and help pull everything together. So in this case, a mine geologist, they weren't able to absolutely step out of the pit and go do local area mapping. They had to get a bit more creative with really going back to something the scale of what's going on in Western North America. But ultimately, it all ties together, right? And you're able to bring it together and improve your local deposit scale model. Rule number 6, sticking with the structural theme, as you can see, I believe starting with a structural skeleton will make your model better and make modeling a lot easier. If you understand the structural regime, as I've been talking about, the major faults, the folds, hinges, prior to trying to work out lithologies, stratigraphy, especially secondary things like alteration and mineralization, again, your result's going to be a lot better. The reality of lacking quality structural data, it may be, this step might be easier said than done in a lot of cases, honestly. Some sites just don't have it. But where you do have structural data, creating the structural skeleton first will vastly improve and help sort everything out, I find in most cases. So here's an example of this. Where on first review, a base metal deposit, you try working this thing out, and it's absolutely a dog's breakfast. It's grade, faulting, lithologies, all put into a blender, mixed in with whatever. Just a bit of a mess. So instead of trying to figure it all out at once, we don't want to boil the ocean here. We want to take it one piece at a time. So let's focus on structure. Let's work this out first. So using drill logging, relogging in some cases, some limited outcrop data that was quite helpful, a lot of public information, geologic maps that were done in the past, so on and so forth. You start to get an understanding of regional structure and regional regime. Deposit scale structural setting was really could be worked out. You kind of go from the outside to the in, as you remember one of the previous steps. It wasn't easy in this area. It took a lot of work because of the multiple orogenies where you've got thrust, normal, strike slip faults all within one area, along with a variety of macro and micro scale structures to kind of confuse things. But really, again, working out those structural controls, the lithology started to fit together, actually. It's a bit like a puzzle piece. That original setting could be worked out. And then once you've got that, now all of a sudden you've got potential conduits for mineralization. The timing of mineralization started to make more sense, and everything started to fit together. And ultimately, you get a better model out of this. Rule number 7, keep it as simple as it needs to be. There's a fantastic quote that I love. It's attributed to Einstein a lot. Not sure if he actually said that, but the quote goes, if you can't explain something simply, you don't understand it well enough. And I think that's a fantastic way to look at models. Really, a similar philosophy should be taken when you do geologic modeling. The simplest explanation of geologic complexity is usually more correct than an overly sophisticated or complex interpretation. Now, if you're a structural geologist, you love to get into the details, but a lot of times that might just add more time and unnecessary complications. So because something is simple, remember, it doesn't mean that it's wrong. We go back to a model being useful. And also, what is it going to be used for, right? Again, we keep falling back to that point number 1. So creating a mineral resource model for say, a consistent deposit. So Lake Superior type banded iron formation deposits, whether in North America, Western Australia, or other parts of the world. Now, in some cases, these can be pretty straightforward from a big picture. You get into the details, there's second order parasitic folding. They're quite interesting, right? But it may be irrelevant for say bench scale mining. You see minor faulting, small offsets, thin dikes, post Post-mineralized calcite veinings that are like 1 centimeter. It doesn't really matter. You're not going to try to model that stuff. And small variations in thickness. What is this going to be used for? Resource modeling, big scale. Keep it simple, keep it straightforward. Don't try to get too complicated with this. Number 8, the waste. So everybody loves shiny things. We're in mining. Going after precious metals is exciting. But moving big piles of dirt, yeah, not so much. So, oftentimes in exploration and mining, geologists are really, really focused on the ore body, as they should be. But then as a result, you may fail to dedicate enough time to actually characterize the waste. A wise mining engineer once told me that, we move a lot more waste in most cases than ore. So, we probably need to understand that stuff. Compounding this problem of neglecting the waste is the fact that, drilling and evaluation work is usually focused or overly focused solely on the ore bodies. So in some cases, getting a hole out in waste, though it may be called a dry hole or a failure, they can be extremely valuable information. So don't just throw it off, don't log it, don't assay it, whatever. But if you can work out stratigraphy, lithologies, and unaltered material, this is a fantastic opportunity. In many hydrothermal environments, porphyry environments especially, or epithermal environments where we see a lot of alteration, and we get things like stockwork, enrichment, leaching, really you end up with some very altered, unhappy rocks, right? And these can be tough ones to work with. So for exploration targeting, it's fantastic if you can work out alteration, but if you're trying to make a model based on protolithologies and structure, you need to step out into the waste, right? So not only getting a chance to look at the waste and seeing what is going to be potentially mined there, but that might actually help you work out what is the lithologies, what was the original parent rock, and the structure of the area. So going back into rule number 2, get to know the geology, and that doesn't mean just in the ore body. Number 9, so reconcile in 3D. So even though many of you on this may work on paper, tablets, screen, sections, or whatever, reality outside is actually in 3 dimensions. And ore bodies are in 3 dimensions. So, when you build your wireframes, you've got to take that into account. It doesn't just happen in section in one direction. Sectional interpretation, this was really standard in the industry probably as recently as 10 or 15 years ago. But when you see sectional interps, be careful. I'm not saying it's bad. I'm not saying it's good. I'm just saying that things need to be looked at in 3 dimensions. Now, notorious in these are elongated ore bodies, large stratigraphic ones especially, where the modeler uses sectional interp along strike and they fail to go back and actually check against long section or plan view. And you get these fantastic, I like to call them grandma's curtains, where one section is up, the next one's down, the next one's up, the next one's down. And you look at it long and it just goes up and down. And that's not actually what happens. And so you really need to check that. Now, there are things like implicit modeling and some of the softwares I mentioned before that do a better job of this, but it means still you need to cut the model and look and make sure, no matter what direction you cut it in, whether it's in section or plan, that it actually adheres to the data and that you have a true 3D model and not just 2D polygons that are extended out into a 3rd dimension. Quick little example here. So on that top section, everything looks pretty good. Some bending and folding, that's okay. But there's some faults in there. And the way that these were done is using kind of a grid algorithm. But what happens with that is once you cut it obliquely along these faults, the lower image pops up and you see these absolutely crazy structures. Is these mountains or faults or what's going on? And when you get that, it absolutely destroys your block model. So things like that, you've got to check. So for my last rule of thumb, this is all about verifying and validating the model. Seems straightforward. I think people should spend more time on this for sure than what I see. It's step number 10. It's you can argue it's higher than that, but it tends to happen at the end, right? So I put it at the end. But with any work product, the modeler really needs to verify their assumptions, make sure what they think went into the model is actually what came out of the model. So when you extend that fault out, Was the resultant offsets what you hoped for? Did the software do what you thought? Now for validation of a model, now this requires new data, right, to test the hypothesis that you're actually trying to put together. So in mining, we mentioned before, production reconciliation, pit mapping, infill drilling. These are good ways to test and calibrate your model for future updates. In an exploration sense, a lot of times just some new drilling or perhaps something as cheap as trenching can be used, or some surface mapping to help validate your the quality of your data. Another key step of this is getting somebody else to look at it. Man, peer review is so underused and such an important tool. That fresh set of eyes are some of the best validation tools out there. Having to walk somebody else through your model, tell them your rationale, your methods, spin it around in space. Does it adhere to data? Don't ever create a model in a vacuum. It should never be a single person who's doing this. And the process is really check, modify, check, calibrate, check, keep checking. And with some of the new softwares, there's some fantastic tools available in them to help verify and validate some of your models. This can be one of the big benefits of implicit modeling. You can actually compare different parameters of the implicit inputs to look at volume and relationships. You can look at probabilities when you're using grade or indicator shells, along with reliance on trends or anisotropy, spatial continuity. So it's always good to look at also how far your data is modeling from an economic importance on these volumes or zones. On the edges, extrapolation is kind of a bad word, but in a lot of cases you do extrapolate the volumes. Typically, you want to do on a rule of about half the drill spacing beyond that last data point, unless you've got some convincing evidence to do something else. And I always like that old adage that really, if you want a tightly constrained model with a very conservative grade volume, have your mine geologist do it, right? And this way, reconciliation is always on the positive side. Everybody loves the mine geo for delivering more ore, lots of back slaps and big bonuses. It's great, right? But alternatively, give your model and interpretation over to the exploration geologist, and they're sure to find the next Escondida about 100 meters away from your last drill hole. So, somewhere in between is probably closer to the truth, but more input and different people looking at it can certainly help calibrate it. So I'll wrap up here, wary of time, but a few takeaways I'd like you guys to have with it. These are all general suggestions. They're not hard and fast rules, and when I have rules in quotes, it's absolutely that. Obviously, through this, try to give you guys the impression. Geologicals, they're important. It's not just a tick and flick exercise you do once a year. Don't take them lightly, and make sure you give yourself enough time to do them well. Understand those use and the customers of the models. Don't overcomplicate it or try to show off how bright or special you are, or some new whiz-bang thing the software can do just because it can do it. And always make sure you're using your brain. Do these things make geological sense in the small and the big picture? And lastly, get these peer reviewed. Check them, repeat it, have somebody else take a look at it. I think with all these steps, you follow them, understand them, go through it. We're going to see a lot better models across the industry. We're going to see a lot better from a risk and a confidence point of view on geology. So thank you very much. I'll turn this back over to Jackie, who's probably got a few questions.
Thank you so much, Eric, for sharing your expertise with us. That was absolutely fascinating. Would like to open up the question and answer period for our attendees. Please use the chat panel to send me a question, and I'll read aloud to Eric. Our first question, our attendee notes that CIM definition standard resources require, quote, exploration and sampling of the ore body. The question is, how do you interpret this requirement? Can one estimate or undercover without drilling?
A very good question. Now, with the CIM standards, we're specifically talking about confidence associated with mineral resource, right? And I mentioned briefly before, measured, indicated, and inferred. Now, with CIM, the category of inferred mineral resources is a good catch-all that tells you you've got some reason for geologic continuity. You've got some evidence that there is mineralization and continuation of mineralization and whatnot. Now, that evidence is assumed in most cases. So in some cases you can, if the evidence is compelling enough, to create an inferred mineral resources based on very limited data. Now this might be from mapping projected at depth, maybe supported by geophysics or something of the nature. But realize that the mineral resources are based on grade and tons. Now, without drilling, it's awfully hard to get any sort of grade information, right? Now, you can have a volume, you can have a shape, you can have assumed density and things of that nature, but you can't have a mineral resource unless you've got hard data that gives you some sort of information on the grade. I hope that helps explain that question.
Thank you. The next question is, can you comment on methods to quantify uncertainty associated with geological modeling and how it ties into resource modeling uncertainty?
Yeah, absolutely. This is a fantastic question. We're seeing more and more within the industry the classification of mineral resources, especially for producing mines, to be done in more of a quantitative method based on, say, production or conditional simulation is another one that's used quite commonly. Now, there's a few different things to do. I'll start with conditional simulation. So with simulation, we can run a number of iterations to look at variability of either a category, so this would be, say, geology, or a numeric, say, gold grade or whatever. Now, these are really good tools that can show us areas of our deposit or mine or pit or whatever we have, which are more variable than others. Now, this is a great tool to use to help aid the qualified person to make a decision on measured, indicated, and inferred resources. I should say it shouldn't be the sole reason, but it should help them. It's also a great way to come up with drill targeting. If you know you have higher variability that you can quantify in an area, well, you probably need more data in there. Hope that makes sense.
That does make sense. The next question, is there a preferred method you would recommend for reconciling an exploration block model to a production block model generated by blast hole data?
Yes, reconciliation. So an exploration model and a blast hole model. So I think you're talking about like a mineral resource model looking at a large area versus, say, an ore control, grade control, or short-term model. In these cases, there's actually a lot of fantastic reconciliation tools to use. It really depends on how much detail you want to get into. Blast hole data it's always fraught with problems, right? It's usually poorly collected. It's the data's not very good. The labs are usually operational labs and so on and so forth. But from the scale of a bench or a blast, you can get some fantastic information on contacts, on grade variability, as well as just what the grade, tons, and any other variables you're looking at, say deleterious materials, are happening in that. So you can take that kind of compound it into or composite into kind of a larger area, then take that volume and move it over to your exploration model, for instance. Now, if your exploration model is roughly adhering to those contacts and roughly showing that, yeah, the grade's about the same, then that's a good way of reconciling it and saying, hey, it's actually performing pretty well. What I see more often is actually the calibration of models. So this would be taking your bench or production scale models and flowing it back in to your block model and using some of that information to kind of tweak your estimation, tweak your neighborhoods, tweak the parameters to help you get at least local areas a little better informed. So it's a long answer to a really good question, but hopefully it gave you a little bit of insight there.
Thank you. Excuse me, Eric. I'd like to remind our attendees that the presentation was being recorded. It will be posted on the SME website in the SME store under recorded webinars, you will receive an email from SME letting you know when it will be available for you to download. And I would like to encourage all of our attendees, if you have any more questions, please contact Eric at the website and the email that you see on screen. That appears to have been our last question. Eric, thank you again so much for sharing your expertise with us. Would you have any final words for our attendees?
No, I just thank everybody for taking the time and the patience and listening to me rattle on about a subject I'm quite passionate about. I encourage anybody, shoot me an email if you've got follow-up questions or whatnot. I'm always happy to help folks out. But thanks again, everyone, for the time.
And thank you again for spending the hour with us. This ends today's session. Have a great day.